Hello and welcome to section 2.7. Today we're going to talk about transformation of functions. So first of all, I want to review the 10 basic shapes that you need to be familiar with, and then we're going to move those around on the graph. Alright, so look with me. The first one is the y equals x graph. Y equals x, we call this the identity function. It is our most basic form of a line. You notice that we can tell something is a line because x is to the first and the y variables to the first. When both variables are raised to the first power and no other operation symbols around them, that's always a line. That's our line shape. So, basic line going through the origin, and then we'll move that around today. Second shape is the parabola shape. It looks like a U shape. It comes from y equals any quadratic equation basically, but its most basic form, y equals x to the second. The third shape, the square root of x. Square root of x looks like a little arc shape. Number 4, x cubed, the cube graph, kind of swirls around the y-axis like so. 5, the cube root function, it lays more horizontally. All of these could be verified with a t-table. You could take some time, draw out an xy table, plot some points, and you could verify these points along this shape. But just for quickness, it's good if you kind of have pattern recognition and know that these patterns are going to work to give you these shapes every time. The sixth one I have here is the absolute value function. It looks like a V shape. 7, this is called the greatest integer function. It looks like brackets with little absolute value signs in them. That little symbol means greatest integer function. It rounds actually. When you plug something in for x, it rounds it to the next integer below it. The greatest integer less than or equal to x is how it's defined. You can see that in your book. But say you were plugging in 1.2 for x, it would round it down for y equals 1. If you plug in 1.3, it rounds it down to 1. 1.4 rounds it down to 1. So it makes these little flat lines, and then when you get to an integer, it jumps up. Like when you get to 2, y equals 2, because it is an integer. So y only equals integers, so it flat lines on all the integers, and you have an open circle on the right end to show it jumps up at that integer amount. Then number 8, let's see, can you see that? Number 8, the 1 over x graph, that's our rational function. It's our fraction, most basic fraction function. When you have x in the denominator, a constant on top, this look, that always graphs to be these two curves. You've got a curve in the first quadrant and a curve in the third quadrant. Again, let me reiterate, these are all in basic form. That's what they look like. We're going to shift those and move those because we know sometimes you'll have a number in front of this or behind it, and we're going to talk about what that does in 2.7. Now, all of these were functions. 1 through 8 are our basic function shapes. So I could have said f of x equals. Notice I said y equals. I should probably use the f of x notation now that we're into that in chapter 2, but it's interchangeable. F of x equals or y equals as long as it passes that function test, and these all do. The vertical line test would only hit these once in any place you could draw it. The other two shapes that are not functions, number 9 and 10, just shapes to be aware of, is x equals y squared. That is a sideways parabola. And x equals absolute value of y is a sideways V. Typically, when you mess with the y, if y is to an even power or in absolute value signs, you'll have a non-function because that gives you two different outputs for one x values. So 2 different y values give you the same result. For x would be an x value repeated, which would look like you can see on the graph, repeated vertically. So those are not functions, but just shapes that you may just jot down in your notes to be aware of. Alright, so now we're going to shift these shapes. In 2.7, there are 4 basic rules to be aware of. And so we'll go through each one of those. Just jot these rules down. You can follow along in the book as well. The first rule is when you have a multiplier. If there is a number multiplied on to any of these fractions, onto the x in front of the x, it's going to affect the steepness of the curve. So multipliers affect the slope. or the steepness of your graph. For example, we know it with our line, y equals x would be what I call the parent function, the most basic form of a line. When you put a 3 in front of it, we know that's where the slope is in a line. The y equals mx plus b form we've learned. So this in front of the x is the slope of the line. But it's actually true with all of our 8 shapes that were functions. When you put a multiplier in front of x, it's going to make it steeper or wider. The bigger the number, the steeper it is. But actually when it's a fraction, it makes it wider, and I'll show you that. But anyway, y equals 3x, we know that what would have been just y equals x here is now 3 times steeper. So the y-intercept is 0. You know that would be a 0 y-intercept on the end. Then from that, you would rise 3, run 1, and so you'd have this steep linear equation like so. So steeper. Let's look at y equals x squared, the parabola shape. Let's put a 4 in front of that. 4x squared. It's going to be 4 times faster for its rise, so it's going to look steeper. The curves are going to be steeper. Let's see what that looks like. If I plot a few points, which I'm always happy when you make a t-table and plot some points just to be sure about this. But you plug in 0, 0 squared is 0, times 4 is still 0. So it did not move from the origin. But when I plug in 1, 1 squared is 1, times 4 is 4, 1 and 4. When I plug in negative 1, I get the same result. Negative 1 squared is 1, times 4. Let's plot those points and see how the curve looks. 0, 0. When I go over 1, I go all the way up 4. And when I go back 1, I go up 4. So the parabola just got much skinnier is really how it looks, more narrow. It's a more narrow shape. So the bigger the number, the multiplier, anything greater than 1 is going to make a thinner looking parabola actually. It makes it go up faster, thus that effect. It's stretched. The official word in the book is it stretches the graph vertically. It is stretched vertically when multiplier is greater than 1. Let's call that multiplier A. That's the letter they use for that in the book. And it doesn't matter whether it's a positive or a negative. We're going to talk about what the negative does. It does something different. But just whatever that number is in front, the positive or the negative of that, so the absolute value of the number in front of the x, if it is greater than 1, it is going to be stretched vertically. All right, if we put a fraction in front of our curve, let's do our absolute value curve, like 1/3 absolute value of x. And let's see what that does. So a multiplier again, 1/3. Let's make a t-table, pick some values. That's always a good idea. We plug in 0 for x. The absolute value is 0 times 1/3. So it did not move it from the origin. It just changes its steepness, its slope. So when I plug in 1, I get 1 times 1/3. And I encourage you to do this, plot some points. You plug in -1, you get the same thing. Okay, so let's plot a couple of points and just look at this. 0, 0. Now I know the shape is a V because the absolute value function. Over 1 is up just 1/3, and back 1's up just 1/3. So the V widens out a lot. You see it goes up slower, 1/3 slower. Every time I put something in for x, do the operation, then it's 1/3, so it's less than it would have been for y, so it makes y a smaller number, making it go up slower, so it pushes it down. They call this shrinking of the graph. So when a is less than 1 and greater than 0, so a fraction like 1/3, 1/4, 1/7, 2/7, whatever, a fraction between 0 and 1, and again it doesn't matter positive or negative, it's going to make it actually wider. Or what the book calls is it shrinks it vertically. So it makes the graph look wider would be the way I would describe that. All right, so that's true for all of our graphs. The multiplier in front just affects how steep the graph goes. All right, the second rule is what to do with the negatives. All right, if we put a negative in front of the x, it's going to have an effect, or whether we put the negative directly on the x. I'll show you the difference. So I'll say if it's an independent negative, like y equals a negative sign in front of the whole function x squared, it's going to flip it upside down. So it's going to flip the graph. What would have been our parabola up here is flipped upside down like so. If I put a negative in front of the absolute value of x, that's our V shape. Now it's an upside down V, like so. And again, you could plot some points to see that this is so. Let's do this again. Let's say our square root function. Square root function normally looks like that. But if I do y equals a negative, an independent negative in front of the action of x, like so, a -1 multiplier on the whole function, it flips the graph upside down. Now the better wording is it reflects it about the, that's the x-axis. So we're going to reflect the graph over this x-axis when there's a negative in front of it. So again, write that down in your notes, that an independent negative sign reflects the graph, this is the book wording, reflects the graph about the x-axis, which to me means it's flipped upside down. Alright, now what do I mean by this independent negative? All the examples I did, you just stick a negative in front of the whole function, that's an independent negative. Well, sometimes we have a dependent negative, and I'll show you some examples of that. A dependent negative would be a negative included with action of x, or in the operation of x. So it's inside of the absolute value sign, or it's inside the radical, or it's inside a parenthesis, or it's in the denominator with it, but it's attached specifically to the x only, not in front of everything. So for example, if we were doing y equals a negative inside of the radical, that's what I call a dependent negative sign. Its action is on the x in the operation. It's not just after all the work out here at the end where it makes the y just opposite. It's actually changing the x value before you do the operation. That reflects about the y-axis. So it reflects it left-right. We don't do that quite as much, by the way. You'll notice in your homework problems, we kind of use the first one where we flip it upside down most often, but do be aware that this is also a rule. So that would look like the arc going the other way, flipped over across the y-axis, reflect about the y-axis. Another example, let's say we were doing y equals, what's another one? Negative inside of the absolute value signs. That's included in the absolute value signs. So it's going to flip it left, right. You know, normally it looks like that. Well, when you reflect it, it's symmetric. We're going to talk about symmetry in a minute, but you can't tell it, but that's what would be the rule. It'd flip it that way. But it wouldn't matter because it's already kind of reflected over there naturally. So you can't see it there. Let's say we had y equals negative x cubed. You know, normally that looks like this. So we'd flip it. It'd be that way. All right. So all the graphs are that way. If the negative's inside the action, it flips it left, right. But if it's on the outside of the action, like negative of the 1 over x graph, normally it's here and here, but it's flipped upside down. Now some graphs have some symmetry, and either way you flip it, it's symmetric, and this is another example. Again, we're going to get to symmetry in a minute. But following the rule strictly, that negative flips the graph upside down. So what was up here becomes down here and vice versa. All right. We'll have to continue the third rule on our next clip, so be right back.